In this lecture, we will review the concept of a function, take a look at multivariate functions, and vector-valued functions. I will not discuss the modern definition of a function, but the way we think about a function is that we have two sets. Let's call the first set A. For example, A could be a set of, let's say, 100 cities in the world. We represent this set with a blob like this, and each city in this set is then represented by a dot in this set. Let's call the second set B. That could be, for example, the countries of the world, and we represent that with another blob. A function is then simply a rule that assigns to each element in A an element in B. And it's common to draw it like this with an arrow and write the name, function f. For example, I could define a function which assigns to each city in set A the country that the city is located in set B. For f to be a function, it must assign an element in B to every element in A. And for each element in A, it can assign one and only one element in B. This would be like saying each city must be in a country and a city can be in only one country. The set A is also called the domain of the function. Another way to write this is as follows. F is a function. For each element in the domain A, it assigns an element in set B. When we talk about functions, then the two most important sets for A and B are the real numbers. If I have a function f, which to each real number, that is an element of this fancy R symbol, assigns another real number, then we say that f is a real valued function of one real variable. And this fancy R is simply a symbol for the set of all real numbers. So we have the following notation. F is a function from R to R with the simple example f of x is equal to x. It is also possible for the domain of the function to be subsets of R. For example, if I consider the square root function and I want the function to return a real number, I need to limit the domain to the non-negative numbers. Another way of thinking about a function from R to R is like some sort of machine. Into this machine you feed a real number, which we typically call x, and the machine will then return another real number, which we typically call y. And really the only rule that f must satisfy is that if you feed 4 to this function and it returns -6, it must always return -6 whenever you feed 4 to the function. For example, this function f of x equal to x is this boring parrot kind of function which simply returns whatever you will feed to it. You feed 9, it will return 9, and so on. We can easily extend this idea of a function from R to R by designing a new function which requires not one but two values. So I have a new function here, f, and this function is not going to be happy by you simply giving it one number. It needs one more, and in this case we will call that y. So y is now something we feed to the function instead of something that's returned from the function. Given these two numbers, f will return a number which we call z. We also write this as z equal to some function of x and y. Or we can write f is a function which takes a value in R2. This 2 here tells us that f needs two numbers, but it will only return one number, so we write it like this. R2 is defined as the set of all two tuples, like this. Two tuples consisting of an ordered pair of two real numbers, x and y, such that x is a real number and y is a real number. For example, minus 1, 3 is an element of R2, while 4 is not an element of R2, it's an element of R. When we think about the real numbers R, we typically visualize that set as the real number line, like this, where each element in R corresponds to one point along this line. In a similar fashion, when we want to visualize R square, we think about that as the plane, or a Cartesian coordinate system with one variable along the horizontal axis and the other variable along the vertical axis. Each point in this plane then is an element in R2. For example, if I have minus 1 here and 3 here, then this point here is the element minus 1, 3, which is a member of R2. In this way, for every element in R2, there is a unique point in this plane. A simple example of a function of two variables is this one. F of x, y is the sum of x and y. So you feed two numbers into this machine f, it will add them and return the result. This point here, minus 1, 3, is mapped to the number 2 by this function f. The way you should think about a function from R2 to R is then as follows. You start with R2 being a plane and R being a line like this. What f does is to map points in R2 to a point in R. Any point in the plane is mapped by f to a unique point along this line. So here is this example again, a function from R2 to R, exemplified by the function which returns the sum of two numbers that we feed to the function. Again, it's not necessary for the domain to be the entire plane R2. It could be a subset of this plane. For example, the first quadrant. We can easily extend this idea, creating functions that do not accept two numbers, but in general accepts m numbers, where m is a positive integer. Such functions are functions from Rm to R. Again, just keep in mind it means that you need to feed it m numbers and the function will return a single number. One example would be a function that accepts m number, sums them, and returns the answer like this. When we deal with functions of several variables like this, it's common to simplify the notation of the function and write f of x instead of f of x1, xm, if you explain that x is an m vector. Some authors might then make x bold while keeping x with the subscript non-bold to remind you which symbol represents a vector and which symbol represents a number. For a one variable function f of x, we say that it's a linear function if I can write it like this, a plus bx where a and b are constants. A is called the intercept of the function, while b is called the slope. The definition of a linear function when we have several variables is then as follows. F of x comma y is equal to a plus bx plus cy, where in this case a, b, and c are constants while x and y are my variables. Extending this to the case where I have m explanatory variables like this, then we say it's a linear function if we can write it as a0 plus a1 x1 plus and so on all the way to am times xm. For multivariate functions, it's quite common to skip the intercept and say that this part, that is a linear function. In this notation, we can actually make a1 into the intercept by requiring that x1 should be equal to 1. Considering the equation on the right hand side, we see that this is precisely the dot product of two vectors a and x. Specifically, if I write a as a column vector with a1 through am like this, such that it becomes m by 1, and I do the same thing for x, it's x1 through xm, also m times 1, then the right hand side here of this equation is the dot product of a and x. We can also write this as a transpose multiplied by x. Checking the dimensions of this, a transpose is 1 by m, x is m by 1. These two match, so that's okay. And the final result will be 1 by 1, which is exactly what we're looking for, as our function f must return a real number. Here is this important example again. A linear function of m variables may be written as a prime x, with a and x being column vectors. So let's move on to vector valued functions. So the idea is the following. Let's say that I have n functions called f1, f2, all the way through fn. And each function is a function from Rm to R. That is, each function takes m numbers and it returns a single number. The functions need not be the same. That is, for given m numbers, the functions may return n possibly different numbers. So let's stack these numbers, these n numbers returned by these functions, into an n by 1 column vector, and we call the result f of x. Well, starting with m numbers x1 through xm, I feed these m numbers into my n functions, and these n functions will return n numbers. Well, that means that my function f is then a function from Rm to Rn. It accepts m numbers and it returns n numbers. And we say that f is a vector valued function. Here is an example. I have two functions, f1 and f2. Both of them, f1 and f2, are functions from R2 to R. Beginning by two numbers called x1 and x2, f1 will return one number and f2 will return another number. Stacking the numbers returned by these two functions into f of x, and I have a function from R2 to R2. For example, for x equal to, let's say, 1 minus 1, f of x is equal to 3 minus 1. Probably the most important function from Rm to Rn is the linear function given by A times X, where A is a matrix, an n by m matrix. We can easily check that this actually is a function from Rm to Rn. If I have f of x equal to A times x, and A is n times m, and x is m times 1, matrix multiplication allowed, and we see that the result f of x actually is an n by 1 vector. So that means that starting with any m by 1 vector x, f of x will return an n by 1 column vector. We also know that A times x is the left-hand side of an n by m system of equations. That is this part here, that's A times x, and we clearly see that each row is a linear function of the x variables, and this is why we say that the function f is a linear function. You can check that you can actually write your function f of x as a1 comma dot. Remember, that is the entire first row of A, and it's n by 1. If you do the dot product of that row with the entire x vector, you will get f1 of x. Similarly, all the way down to a n comma dot multiplied by x.